I'm back with another 3D printable key switch update, and here's the latest. I'm using I'm back to PETG for the main switch body and the return spring, because so far it's been the best feel, even though it loses its strength over time. But I think I can work around that. And I'm using this is Taulman Bridge Filament as the beam spring. Now the beam spring is kind of important because it's going to go in and out a bazillion times, so it needs a very high fatigue index. And that is the thing that, it's basically the term that you use for a plastic that can bend a lot of times before it wears out, basically, before little cracks develop and things like that. And nylon is one of those filaments with a very high fatigue index. It can withstand a lot of bending and still return to its original shape. Over a long period of time. And this one feels it's too much force is required, but I can fix that. That's just parametric, right? That's parameters. So I need to make a slightly thinner beam spring, and I've also got some Taulman PCTPE to try as a beam spring as well, and that might be a little bit softer and give me a more gentle feel. But check this out. This is the reason why I'm making this video. So I figured out the calculations, and this is really hard for me. I'm not a mathematician, but I've actually figured out how to calculate the bend of the curve using a math formula that was invented in 1998. That's like cutting edge math. So let me explain this for a second. So the beam spring has a bend in there, right? It's an arc, but I need to print the spring flat, right? So how do you determine how the length of the flat spring and how it's going to fit inside there with the arc? So I've figured it out. Like, you just say, all right, I want like a 2 millimeter bend, meaning the sagitta of the arc. So if you have an arc like this, the point at which it goes from flat to the top part of the arc is called the sagitta, right? So the sagitta of the arc, well, actually, that might be the chord. Never mind. It's one of the chord of the sagitta. Anyway, so this is actually it's called the quarter tank problem, because it's like a circular tank of gas. And if you stuck a dipstick in, how would you tell how much gas you have based on the area here? And part of that formula was figured out by these guys in 1998. And apparently, it's a very big deal for them figuring this out. So I basically converted their math formula to OpenSCAD, which was so hard for me. Like I said, I'm not a mathematician. Math symbols give me a hard time. So I actually figured it out. So you can actually just plug in OpenSCAD, you say how much of a bend you want, like 1.5 millimeters. And this is a very obvious way to control, like, the tactility, the point of tactility. So 1.5 millimeters means you're going to have to go down 1.5 millimeters before it inverts itself. Right? Very simple. So you can control how it feels that way. And the strength of the spring is going to be based mostly on the material and how thick and wide it is. And I haven't figured out those formulas yet, but I'll print out a whole zillion of them, and I'll provide a table when I finally publish this, with certain grams of force and whatnot. But the key that I wanted to show today, which is super important and so awesome, is check this out. So this is a 1.5 millimeter bend. So I just went down probably 3 millimeters. Because it gets to the halfway point, inverts itself, and then it's basically effortless past that, except for the return spring's strength. So it's like boom, and then it stops there. But you can continue on the extra millimeter, because it's a 4 millimeters of travel parameter. See that? So pop, and then you can continue on. Now it's a little bit. I printed this one. It's a little too tough. I need to basically thin out this spring and just push this. It's PETG, so if I just press this a bazillion times, the return spring on the top will become, it will lose a lot of the force required, but it should level off. It's not going to lose strength forever. It basically, PETG, the way it works is you start off with a very strong force, and as it bends in and out and in and out and in and out, it will eventually lose a certain amount, probably 60% after, say, 1,000 bends or something like that. And then it just gets lower and lower and lower, and it's sort of this long curve that levels off around 50% and stays there for the most part. That's what it should do anyway. Of course, it depends on the brand and all this other stuff. But I just need to play with it for a while and see how it winds up in the end. So if I have to make a key switch that you have to break in, that's okay, because you just fidget with each switch for like an hour or two for a few days, and that should get you covered. Or just put it together and then just type on it for a while, and it should break in and eventually settle down to whatever force curve that you want. But I'm still investigating different materials for that return spring, that orthoplanar spring at the top there, which again was fancy math that I had to figure out. I'm not a mathematician, but I think it's coming along nicely. I'm actually very satisfied with this result. It's a good thing to wake up in the morning, pull it off the printer, assemble it, and have it work out. And that's it for now. I'm still working on it. And now we still have that tongue flapping action.